Good morning, student. In last lecture, we have to see the single line representation of the every equipment is related to power system. We have to see the what is the generator single how to generator. We have to denote in the single line diagram what parameter is specified with the generator. What parameter is specified related to transformer and transmission line and load. Now we have to see the what is the main assumption or main the parameter or main things we have to assume in the when we have single line diagram representations. So we have to first assumption is the three phase balance operating condition is a considered. So whenever we have to represent as a single line diagram, we have to consider as a all three phase are in the balance in terms of the uh, voltage angle, current angle, voltage magnitude, voltage impedance, as well as current magnitude. So we have to assume the operating condition is a same only whenever we have to consider as a single line representation. Second one is the transformer impedance is indicate on the appropriate side. Whenever we have to connected in the transformer as a transmission line, we have to see the first of all which side we have to consider as a first single line representation. If we have to consider first as a primary side, so we have to appropriate indicate the appropriate impedance in the primary side, as well as we have to use in the secondary side. So we have to only appropriate indicate the appropriate impedance in the secondary side. So this topic is the most important. Which side we have to indicate the impedance of the transformer. And third one is the transformer magnetizing reactance is the neglect. Because of the why we have to magnetizing reactance in neglect, because of the magnetizing reactance only occur when the transient clear. So first time we have to analyze the transformers, otherwise the any fault are occur, there will the only the magnetizing reactance is occur. After that there will be negligible, otherwise we can say this is 0.00 something, so we have to neglect it. Fourth one is the generator is represented as a voltage source with the series impedance. All the generator, there will be maybe induction generator, there will be the synchronous generator. All the generator is the represent as a voltage source with the series impedance. So we have to identify the what is the winding resistance of the or winding impedance of the generators. And for fifth one is the transmission line is a represent with the pi model. You have to also use the what is the pi models and so what is the T models. In a power system one, otherwise you are not studying power system one. We have to continue in the power system two. So all the pi models, why we have to use the pi model? Because of the pi model, only two terminals are considered whenever we have to find the admittance. I will draw some so you can easily understood. And this is a transmission line. So we have to all transmission line impedance we have to denote in middle of the transmission line, and the half of the capacitors is denote in the sending end, and one of the half of the capacitance we have to denote in the receiving end. This is a receiving end, and this is a sending end. Because of the why we have to use, we have to also use the T model. Because of T model, what is the measure difficulty in T model? In T model, the impedance is half of both terminals. So we have to the capacitance is full capacitor denoted in the mid of the transmission line. But we have to find whenever the voltage across capacitors, we have to find the extra effort to find this terminal voltage. But whenever we use the pi model, we have to the this terminal voltage is equally to the sending end voltage, and this terminal voltage is equally to the receiving end voltage. So we have to not done the extra effort for the finding of the two terminals voltage. But whenever we're talking about the current is the same in the series connections, but there's a voltage we have to work is easy for the finding two ends voltage, but here we have to done by extra effort and finding the midpoint voltage. So we have to, whenever we talking about a single line representation of the any transmission line, we have to only represent in the pi models. So next one is the load assumed is a passive and represented by the equivalent impedance. You have to study the what is the active and passive load. So active and passive loads we have to only consider as a passive load because of the all load are the consumption of the power. It doesn't not matter if we have to what is the extra reactive power is consumption or not consumption. So here you can only assumption of the passive powers or passive loads. And last one is the neutral grounding impedance does not appear in the single line diagram. Here you can say the in last lecture the neutral grounding impedance is not does not matter. Whenever we have to work in our neutral grounding, there is the reactance grounding, so we have to ground denote here to the x is a 1.5. But when the neutral is directly ground, we doesn't not matter okay, what the x value we have to, otherwise impedance or reactance value we have to sin. So whenever the neutral is grounding, so single line diagram does not matter to denote this grounding. But neutral is grounding to the some impedance, reactance, or otherwise some resistance. So this need to denote the this the value of the impedance, reactance, or resistance. What we need for the neutral grounding. So you can hear the one example of the all the representation of the line. So I will the all the first of all this first diagram is the representation of the single line diagram of the whole power system. This is the generating unit. This is a bus system. The box is the circuit breaker. This is a transformer, transmission line. Another transformer is the bus bar, and the load is the load. So I will use for the single line diagram of the one phase. So one phase is the single line. This is round shape with the voltage source. So we have to as a voltage source with the impedance. So resistance and inductors are the impedance. The load, so you can easily understand. Okay, and this is the impedance of the generator, and these are the transformer per unit per phase system. And I will show in the previous slide the pi model of the transmission line. This is the pi model of the transmission line for one phase. Okay, and this is the another thing. You can represent the whole box with this box. This box is this box, and these are this box, and this is the. So you can easily, and the second transformer is related to this, and the one here you can see the one generator are connected. So this generator are connected in parallel with the series impedance. This is the series impedance. Okay, and these are the load. This is the load. So load are connected to the parallel of the transformer or generator. So load is connected here, but is a load is a maybe a only megawatt or not one unity power. So you can easily directly show in the resistance, but it's some lagging or leading. If you are the leading power factor, so you can denote here the resistance or capacitance, and as well as it's a lagging power factor, so you can denote the resistance and inductance. It's easy to understood the what is the behavior of the load. This is the single line diagram of the one phase. We have to further specified and further example using this, so you can easily understood what is a single line. This is just example. We have to see in the next examples, many of examples, so you have to much more idea about the single line representations. Now we have to see the what is the per unit system. Here you have to see the per unit system. So first of all, we talking about the why per unit system is needed. In the you have to see the power system, whole power system. There is the different voltages, different current rating, different voltage. resistance frequency is the most of common, but we have to plan the one nation one grid. So frequency will be a change in India to Australia and Australia to US and New Zealand. Some frequency are there, some have a 50 hertz and some have a 60 hertz. So we have to use the per unit system. So first of all we talk the why per unit system. I am talking about previous in the something everything is the difference voltage rating, current rating, MVA rating, megawatt rating. But we have to consider the one nation, one grid. We have India in a one grid, one grid. There will be a one grid if we are talking about the connected to a one grid with all load and all power system, all or generator. So we need to one specified rating of the all equipment, all voltage rating or all current rating. So we have to use the per unit system. Here we have to talking about the only things. The power system equipment rating are expressed in the megawatt, MVA, kV, kiloampere, and ohms in hertz. So express all these quantity in per unit system in percentage of the reference base value. If you are considered in India, the reference base value of the power consumption is some gigawatts or some megawatts, whatever you have. But so all we have to find out the percentage of the from the this reference value, this gigawatt or megawatt. So we have to easily find out the what percentage this generator or what percentage this load is consumption of the voltage hours, power or deliver of the power. We have to easily find out. Per unit method is simple and more informative than the use of the actual value. We have to see how can the more informative or useful for the calculations of the any system. Here is just example for the selected base value is the 101 kilowatts and the 66 kV, 101 kV and 132 become a we have to see what the 100 110 is kV is the base value. So how can we 66 kV denote? The 66 kV denote is 0.6 1.1 sorry 101 kV is the 1 and 132 is the 1.2 per unit system. So it's the 60%, 100% and the 120% of the base value. This is the base value of the 60 is the 60% and the 101 is the almost 100% of the base value. So how can we have to find the per unit value as a distance? So per unit value is the actual value of the quantity in any unit. So actual, what is the actual value here? This example we have to find. So 66 here the actual value and the base value. What is the base value? 101 kV is the base value. So we have to directly find out. If you are 66 divided by 101, 110 kV. So you have to find the per unit system of the this. Now we have to see the power based on the consider MVA and voltage based the consider in the kilovolts. If you are talking about any transformer or any system, there is the two ratings. One is the power rating, it's called as MVA, and the second one is the voltage rating, the kilowatt. For voltage, current, and impedance, if any two are selected, is the base value. Third one is the automatically in the base value. If you are considered the current, voltage, current, or impedance, only two quantity we have to consider the base value. We have to consider the base value. Third one is automatically converted into base value because of the according to Ohm's law. What is the Ohm's law? R is equal to V by R. Sorry, I. Otherwise, I is equal to V by R. So V or I we have to find in the per unit system. R is automatically per unit system. If you are considered as a V or R is a per unit system, I is automatically we have to find in the per unit system. So don't need to find the all these things is the per unit system. We have to find only two things in the per unit system. Here you can find the some formula for the finding the per unit system. So base voltage ampere or we have to take kVA rating or transformer rating is some MVA is the base value and the base voltage is some base voltage is 11 kV, 166 kV, 33 kV. What is the base value? So what is the base current? So base current is a IB is equal to MVA base value and the KVA of the base value. So we have to this denotant because this is MVA and this is a KVA. So we have to directly don't know find and we have to cancel out by 3. So it's a 3. So per unit voltage is the I actual divided by base value of the current. First of all, we have to find the base value of the current, and the base impedance is the base voltage divided by base current. So what is the base voltage and base current? Here we can find is equal to kV into multiply by kV set. So we have to IB equation. What is the IB? We don't have to find. So directly this equation we have to consider it. So denominator is considered as a denominators, and we have to kV square divided by MVA. So we have to directly find Z per unit is equal to Z actual divided by Z base. We have to find the Z base from here. And what is the Z per unit system is equal to also we have to find IZ divided by V. So IB is equal to 1 by V. We have to find this. So here we can see the also what is the require of the bring the per unit impedance each equipment to new common power base. So all something we have to track up the one system is connected to another system. Otherwise, we can call this a interconnected system. So we have to how can find the new base value of the impedance current or any another quantity. So we have to first denotance. What denotant base is the use? So MVA all this the base MVA of the individual equipment, any individual equipment, and KVB all the base kilovolt is the any individual equipment. So all the things we have to mention here, you can done by your own self. And the per unit impedance of the equipment is the own base value. So new, how can be is the new is the new base value we have to find and the old base value. So what is the per unit impedance of the new from the after the interconnected with the another system? So Z per unit old by MVA base new and MVA base old multiplied by KVA square base old and KV square base new. We have to find the Z per unit is the new when after the interconnected of the any systems. Up to this here we have to end these sessions. In these sessions the homework is the write down the all the equation related to in previous slide. We have to see in the previous slide the all the equation of the finding of the base per unit systems and per unit current and per unit voltage, and this equation you have to write down your own self, and we have to see the next lecture in the actual impedance how can we consider and the LV winding and HV winding of the transformer. I hope you enjoy this lecture. Thank you.